Hello everyone. Today we are going to see a topic on thermochemistry. Thermochemistry basically deals with the changes in energy in a process where chemical reactions are involved. Let me consider a chemical reaction where methane is undergoing oxidation or nothing but combustion reaction to produce carbon dioxide and water. Now in this particular reaction, a some amount of heat is either generated or consumed as a part of the reaction. In a process, in a chemical process area where the reaction is involved, if the exothermic energy, that is the exothermic reaction occurs, what it means is the energy could be produced as a result of reaction. In that case, it is called as exothermic reaction. There is another type called as endothermic reaction where the energy is consumed as a part of the reaction. Now, if you look at the graphical explanation for this, the reactants are at a higher energy level than the products in the case of exothermic reaction. That means the products are at having a lower energy content compared to reactant. The extra energy, that's the difference between the two in reactant and the products, is dissipated in the form of heat energy, and we call it as enthalpy of the reaction or heat of reaction. In the case of endothermic reaction, the reactants are at a lower energy level compared to the products. So the energy has to be given to the reactant so that the reaction goes ahead and the products have a higher amount of energy. The difference of amount of energy is the amount of heat energy absorbed by the reaction. So the difference between the product total cumulative energy of the product minus the cumulative energy of the reactant is the heat of reaction. This is a basic definition. Now in simple, endothermic reactions consume the energy. If they have to consume the energy, according to first law of thermodynamics, it has to come from the surrounding. So the surrounding loses the energy and gets cooled. It provides that energy to the system where the chemical reaction is going on, the process is going on. The reaction will go in the forward direction. Whereas in the case of exothermic reaction, heat is released. When heat is released, the surrounding receives the heat, because of which the surrounding becomes warm. The temperature of that is increased. Let's define certain heats of reaction. So before I define the heats of reaction, let us see what is reaction condition and a standard condition. Reaction condition is the one where the actual reaction is going on at a particular temperature and pressure. Now, to compare all these values, to have a standard values of heats of reaction, we take a standard condition, means a temperature of 25 degrees Celsius and pressure of 1 atmosphere and pH of 7. At this particular condition, if the reaction goes ahead with all the reactants and products at their standard condition, standard state to be precise, if they should be at their standard states. What do I mean by the standard states is that at this particular condition, if you consider water H2O, if you consider under this condition 25 degrees Celsius and 1 atmosphere pressure, the H2O should be existing in the form of liquid, not vapor, right? So similarly, oxygen, if you consider, it should be existing in the form of gas in this condition. But the realistic situation, the actual condition, the temperature and pressure may be some higher value, maybe 2 atmosphere pressure or 100 degrees Celsius. Under that situation, the reaction may be going on. The information what we have, that is called a standard condition, it will be useful for us to evaluate the actual amount of energy that is actually released under these conditions. Let's see the heats of reaction. Heat of reaction is nothing but enthalpy of the reaction or the energy that is released or absorbed when a chemical is transformed in a chemical reaction. So when a chemical is when the chemical is consumed and the product is produced, some amount of heat is either released or absorbed. That amount of energy is called as enthalpy of the reaction. It's also known as heat of reaction. Why heat of reaction and enthalpy are equivalent here? The reason is we are considering the reactions are undergoing at a isobaric condition. From the application of first of thermodynamics, we have seen isobaric condition Q will be equal to H, in fact delta H, right? Now, if this heat of reaction we consider under standard condition, if you consider this release of energy or absorption of energy under standard condition and all the molecules, products and reactants both are at the standard at their standard state. If that is the case, then we call that a standard molar heat of reaction. So what is the major difference here? We are considering the enthalpy of the reaction same as heat of reaction, but the difference here is it is transformed on the basis of 1 mole of key reactant or a product. Key reactant in the sense we will consider one important reactant or a product which will be considered as 1 mole, for which this entire energy whatever released we will considering, we will write it as kilojoule per mole of that particular chemical, and this reactant product should be present at their standard state under the reacting conditions. So that should be the major requirement. Standard heats of reaction, there are mainly two types what we are going to consider now, but remember there are many other types which we are not focusing on right now. We are focusing mainly on the standard molar heat of formation. Delta HF naught is the notation. Here the dot not, okay, it represents standard. Okay, so if this 0 is not there, that is a degree symbol is not there, then it is not a standard, it's a normal heat of reaction. If there is a 0, that is, this particular symbol, if it is there, that is what it means, it is under standard condition, the reaction is going on. All the reactants and products are at their standard state. Now here the formation, what it means, you have to produce 1 mole of that compound. How? It has to be produced from its elements. From its element, that particular product has to be produced under a standard state. All the element and the molecule which is being produced should be under a standard state at that given temperature. Now, hydrogen in the gaseous form, that is 25 degrees Celsius 1 atmospheric pressure. Oxygen gaseous form. Water at atmospheric condition, it is in liquid state, right? So then I can write it as delta HF naught. If I conduct a reaction where the H2O is in the vapor phase, then it is not standard, it is simply the heat of formation. So that's the major difference between the two things. This is the heat of formation, this is standard heat of formation. When I say standard, at atmospheric condition, standard condition is the atmospheric condition. So all the molecules should be in their standard state. So keep a note of this. Standard heat of formation for any element in their standard state is 0. If you consider any element, for that the delta HF naught is 0. We are taking this as the reference value. Standard state of standard heat of formation for any element is equal to 0. So that's our reference point from where all this calculation starts. So as I told you, one we are seeing is heat of formation. Another one what we will see is standard heat, molar heat of combustion. So in the case of formation, we saw that the molecules will form from its element. Whereas here, that is delta Hc naught, C for combustion, is a standard molar state. So 1 mole of the substance of interest, that is a reactant, undergoes complete combustion. 100% combustion is done. When you have a complete combustion, the product is carbon dioxide and water. Okay, so you have to write a combustion reaction first. That is, oxygen is reacting with the particular molecule, 1 mole of that molecule. All the chemicals are in their standard states because we are writing standard, and this carbon dioxide and water are produced. So in a simple way, write the molecule, reactive with oxygen, products are carbon dioxide and water, balance the reaction with the interest molecule with the 1 mole, right? So the heat of reaction what you get, it's kilojoule per mole for that particular combustion reaction. Similarly for ethane, another value, so it is having 1560 kilojoule per mole. This is an exothermic reaction as you observe. So whenever heat is released, right, that product has lesser heat of energy compared to the reactant. That means it's a negative value, that we call it as exothermic reaction. Always heat of combustion is a exothermic reaction, whereas heat of formation may be exothermic, may not be exothermic. Both possibilities are there for heat of formation, whereas for heat of combustion it is always exothermic, reacts with oxygen, produces carbon dioxide and water. Here I have a numerical for you. You can pause and read the problem. Try it yourself once. If you don't understand, come back. Let me explain you the solution. Okay, let us look at what's the solution of this. We have fumaric acid. and it is being produced from malic acid as per this reaction. We have to find out the standard heat of reaction for this particular reaction, given the standard heat of combustion of malic acid and fumaric acid. So what we'll do is we'll take 1 mole of malic acid as the basis. The reason is we have to find out the delta HR heat of reaction for this reaction. The key point we'll take it as the reactant. Reactant itself is taken as the key element or key molecule. So we'll take 1 mole of malic acid undergoing the reaction. Then by definition, standard heat of reaction is enthalpy of the product, all the products, minus enthalpy of all reactants. But enthalpy of that individually it is not available to us. Instead of that, heats of reactions are given to us. Let us strategize a method to calculate this particular heat of reaction. So this is the reaction which is given to us, and for which you have to find out the heat of reaction which is unknown. Let me call it as equation 1. Let us consider this as an algebraic equation. This arrow mark replaced by an equal sign, right? So I can write one more equation based on the given information. What equation we have, information we are given? Heat of combustion of, standard heat of combustion of malic acid. So malic acid, if it undergoes combustion, what will happen? Oxygen is reacted, carbon dioxide is produced, water is produced. Now balance the reaction. When you do the balancing, first you do the balance for the carbon, then you do the balancing for hydrogen element, then do the balancing, reverse balancing for the oxygen, write the coefficient of reaction, that is the stoichiometric coefficient of reaction for oxygen at the end. So balance the reaction, that's very carefully how to do it. Once that is done, for 1 mole of malic acid, this much amount of heat is released because it's an exothermic reaction given in the data. Let me call it as equation number 2. Also, we are given with the fumaric acid heat of combustion data, standard heat of combustion data. So I will again write an equivalent equation for combustion reaction. That's equation number 3. Its data is given. Now what we have to do is we have to perform algebraic operations. We have to use equation number 2 and 3, manipulate it algebraically so that you get equation number 1, right? So what we can do, we can flip, reverse the reaction number 3. Flip or reverse means what? This arrow mark reverse it, right? We'll write product in the reactant side and reactants in the product side. So it will read like this: 4 carbon dioxide plus 2H2O, arrow mark means producing fumaric acid plus 3O2. Meanwhile, this delta HF, the sign also changes. The standard heat of reaction for this will be plus 1334 kilojoule. Instead of that, let me call it as minus of this value, right? Minus delta H. Let me call that way. Now, if you have that reverse reaction, plus if you add the reaction number 2, you combine them algebraically, means common terms you can cancel out. The way you cancel out common terms across the equal sign, in this case CO2 and H2O are on left side. In the equation number 2, you have them carbon dioxide water on the right side. You can cancel out the common terms. Remaining terms which are not cancelled, if you write it, what do you get? You get malic acid is equal to fumaric acid plus 1H2O, because there are 3 and 1 2 here, right? The difference is 1H2O. 1H2O, you get it. You write it on a piece of paper and try it out. Just reverse the reaction 3, add 2 to that, mathematically add it up, means the way you add the algebraic equations, you add it, you end up with this equation, right? Same way, the delta HR value also get added up. So standard heat of reaction delta HR naught. So equation number 1, reaction number 1 is equal to reaction number 2 minus reaction number 3. Reverse means minus, right? So the same thing I have written here, minus and this plus. Minus for the third reaction, plus for the reaction number 2. The corresponding value I have to take, delta HF value, right? So minus of minus 31334 and minus 1328. When I simplify that, I get 5.2 kilojoule per mole. That is the standard of rate of reaction for the reaction 1. So what do we learn here? We learn that first the data that is given to us, we have to write it in the form of a reaction, algebraically manipulate it. It is possible that we may have to multiply a given reaction with some number. Maybe I may have to multiply it by 2, 3. In that case, I have to multiply the whole thing with that value, right? Inverse we may have to do it. In simple, all the data that is given to us, data means here heat of combustion data given to us, those I have to convert it to some reaction, algebraically manipulate that, right? Algebraically, after manipulating it, you should be able to get the equation 1 or the reaction 1, which is your required equation. Equivalently, the delta H value also you have to algebraically manipulate the way you have written this manipulation, right? So you end up with the heat of reaction for your required reaction. So equivalently, we'll see one more question. This problem, you go through this, you can pause the video, you can read it or write down the problem. Then you can try to do the solution of this. Okay, let me explain the problem for you, what we are trying to do here. So here you have to find out the standard heat of formation benzoic acid, standard heat of formation of benzoic acid, uh, given the standard heat of formation of carbon dioxide and water, right? So heat of carbon dioxide and water, heat of formation data is given. When you say heat of formation, from elements they are produced. Carbon plus 2 oxygen gives you carbon dioxide. That is the heat of formation. Similarly, water, two elements, 2 moles of hydrogen element H plus 1 mole of oxygen gives you H2O. Then combustion reaction for benzoic acid you have to write. Then equivalently their delta H1, 2, 3. 3 equation number 2, equation number 3, equation number 4 you will write. What is the equation number 1? The required one. You have to find out the standard heat of formation of benzoic acid. Means from their elements you have to write it. Their elements giving the benzoic acid. So let us look at that. Since I require benzoic acid formation, the benzoic acid is the product and that is my basis. 1 mole of benzoic acid is produced, right? So either it is combusted, that means under the reactant condition. Here it is a formation. In this case, it's in the product side, right? So it is produced from its element 7 carbon, 6 hydrogen, 2 oxygen makes up 1 benzoic acid. So the standard heat of formation I want to find out, right? That's the requirement. Let me call it as equation number 1. Please note that in reality, this is not the way it is produced. Production is in a different way. It is a theoretical calculation to evaluate standard heat of formation. It is a conceptual evaluation. So let us look at the given data. Heat of formation for carbon dioxide, heat of formation for water, heat of combustion for benzoic acid. It's a balanced reaction. Let us call them as equation number 2, 3, 4. Let us write down their data that is given, that is heat of formation, standard heat of formation and combustion data as per the given information. Let us write down. Next, what you have to do is you have to algebraically manipulate the equation number 2, 3, 4. You may have to multiply some equation with some number and either flipping also required. Overall, you require to manipulate that into one equation, giving you this equation number 1. You can pause at this point. You may try it out further, manipulating this and try to get this. Then you can go ahead. Alright. Now, this is the equation we have written in the previous moment earlier, which equation number 1, 2, 3, 4. So, let us do the manipulation of that. You can multiply the reaction number 2 with 7, reaction number 3 with the 3, okay, multiply throughout with 3 and flip, reverse the reaction number 4 and add them. If you do that, you get equation number 1. It is 7 into C plus 14 into O plus 7 into CO2. Here it is 6 into H plus 3 into O plus 3 into H2O. This is inverse, that is 7 CO2 plus 3 H2O gives you benzoic acid plus 7.5 times O2. When you add them together, you get this equation. You can try it on a paper, cancelling out the equal terms. You get the reaction number 1. Same way you have to perform it for the their standard heat of reaction. That is 7 times the standard heat of formation for carbon dioxide, 3 times for the water heat of formation, and minus because you are reversing it, right? So heat of combustion of what is this, benzoic acid. So substituting their values, you get minus 380 kilojoule per mole after simplification of terms. So that's the standard enthalpy of formation for benzoic acid, minus 380 kilojoule per mole. In summary, what did we learn here? We have learned heat of reaction, that there are two main types, heat of formation and heat of combustion. We have also learned standard states and how they are useful in evaluating some standard heat of formation or combustion of some other reaction given one information. So we have solved a numerical on calculation of heat of reaction given the data on heat of formation or heat of combustion. Here I have a numerical for you. You can try this equation, try this numerical. To give you a hint how we are going to do this, we may not be knowing the molecular formula for NAD, NADH and acetaldehyde at the point time. It's a heat of formation data that is given. All are formed from their elements. Please note that when this reaction is balanced, their heat of formation, okay, so it gets cancelled out. So you are using 1 mole here. So whatever elements it is being produced, same way overall it is the same, because the number of chemicals, I mean elements on this side will be equal to elements on the other side, right? So elements that form NAD, elements that form an ethanol, when they add it on the other side, it gets cancelled out. In simple way, all elements in the reactant side, okay, elements, all reactants, you can say reacting elements, you can say arrow mark NAD, 1 mole of NAD is produced. For that the delta HF is minus 10.3. Same way for ethanol, all reactants for ethanol, arrow mark ethanol, all reactants for NADH, arrow mark NADH. What is that molecular formula? You may not know it, not necessary. Product is NADH, for which the delta HF is minus 41.4. Similarly acetaldehyde. Now when you invert that, reverse that, that means NAD and ethanol you may have to flip, NADH and acetaldehyde you may have to keep it as it is. When you add the 4 reactions, right, 4 equations you have, when you add them, you get this equation, for which you have to find out the heat of reaction. Remember, for this heat of reaction, it is all are 1 mole, right? So whatever you get kilojoule per mole, that means when 1 mole of ethanol reacts, that much amount of heat is either released or produced based on whether it is plus or minus. You have to find out that under equation number A. For question number B, you have to find out for 10 gram of ethanol. If 10 gram of ethanol is completely converted to acetaldehyde, how much amount of heat is produced? So 1 mole of ethanol, when it is reacted, you get that much kilojoule of energy, right? 1 mole of ethanol means 46 gram. Mole multiplied by molecular weight gives you gram. So 46 gram of ethanol, when it is reacted, that much amount of energy is released. So if so, 10 gram of ethanol is reacted, how much energy is released? You can calculate using the cross multiplication method, right? So that is how you have to solve the problem. Very similar to that, you have the problem number 18 and problem number 19. So you try these 3 problems yourself. Here in this problem number 18, you are not given with the reaction, you are supposed to write the reaction. So you are given the numerical in a word problem. So you have to convert this into chemical reaction. Part B, what is given is, if the 50% of energy what is available there, released, whatever is available, if it is used to do the mechanical work, and 25% of the energy from the eating 1 mole of glucose, it is used for climbing the energy, right? This is general explanation. First sentence has nothing to do with the second problem. Here is the maximum value. So say that 1 mole of 1 mole of glucose is consumed by one person, some amount of energy is available, 25% of that, that is part A, what you get the answer, right? So 25% of that, that means 0.25 into that much amount of energy. If it is used to climb a mountain, how much high he can climb? So we have an equation that energy will be equal to potential energy, right? mgh. Mass we know, gravity you know, height is the question. Energy is 25% of this energy what you get, because here it's per mole of glucose, right? You will calculate per mole of glucose. For 1 mole of glucose only it's asked here. So you have to find out the height to which he can climb. So the energy, 25% of that is used, 0.25 into that energy which is produced out of 1 mole of glucose will be equal to 70 kg into gravity into height. Height is the unknown, you have to find out. Now this question number 19 is exactly similar to question number 17, but there are 2 equations that you have to tackle here. Alright, so 2 equations are there. You have to find out the standard heat of reaction for this third reaction. So 2 reactions are given, their standard heat of formations are given. Manipulate the reactions, try to solve, try to find out the heat of reaction for this particular reaction. So here we learn solving the problem, the assignment problems what I given you. You are trying to solve the problem without knowing their element from which they are produced, right? That is more easier, for the reason that they are 1:1 ratio. It becomes a little easier to solve this kind of problem. Yeah, that's it for this class. Thank you.